Swayam Prabha. Digital India. Educated India.
Welcome back, my dear friends. A very good morning, good afternoon, good evening to all of you who are all of you are taking this TQM2 course under the NPTEL MOOC series of lectures. And I am Raghunandan Sengupta from the IME department, IIT Kanpur. If you remember that we had just started the concept of factorials and factors based on it. The factors are not based on which your analysis would be done, not the ANOVA analysis. Is basically further on where the factors are in such a way that some of them are quantitative variables, some are qualitative variables. Based on this, we will try to analyze how the combinations could be done to find out the best effect from those. And obviously, we will go for to find out the total squares, sum of the squares, then the degrees of freedom, then the mean squared errors, and finally test the hypothesis depending on the level of significance which has been already been stated in the problem, whatever it is. Now, in this for an example, if you consider, say for example, the battery problem. So, in the battery problem you had a type of material. So, material would not be, the type of material can be divided on a qualitative framework, like say for example, the quantum of magnesium is more, silicon is more, or say for example, carbon is more, whatever the factors be, or it may be the amount of impurities which may be needed. Say for example, I am doing the doping experiment in physics, and I need to basically add some impurity in order to basically change the conductivity of the material. So, the amount of impurity may be there, or say for example, you are doing some osmosis experiment and then the density would change. Those are in a sense qualitative in nature. And if you consider the temperatures, so they were basically temperatures at the two end, one was 70, 125 and another was basically 15. So, when you are trying to do that, you will also try to understand these are quantitative in nature. So, trying to combine the quantitative factors and the qualitative factors would basically done in such a way that we are able to do a one-to-one correspondence between them, such that overall picture and overall analysis can be done in the best possible manner. So, to continue that in this 23rd lecture, we will basically delve into these problems in more details. So, if you remember, consider the general model would be same, a simple regression model. And what was the simple regression model? Consider you had basically three factors. I am talking about those factors A, B, C. So, you had three factors, capital A, capital B and capital C. So, Y, I, J, K. So, I would be for A factor starting from 1 to small a, J would be for factor B starting from J is equal to 1 to small b, K would be the factor corresponding to C starting from 1 to small c, and the last suffix under Y would basically be the L, I, J, K, L, the fourth one would basically simplify or denote the number of samples which you have basically starting from 1 to small n. So, if that Y I J I want to find the effect, that would basically be equal to mu. Mu is basically the averages of the averages. So, you would basically take the averages for A, averages of B, average of C and average of n, and then find out mu, which is the so called the population expected value. And if it was not available, you will try to replace that with mu hat, which is the best estimate. Then the other terms which would be very logical come out from those analysis would be tau suffix I. I will repeat it and then come to that again. I know I am basically repeating the same example time and again, but it will make sense why these changes are being done in the factorial design models. Then you will basically have tau suffix I, then you will have beta suffix j, and you have basically gamma suffix k corresponding to the dispersions of the variations which you would have for the A factor, for the B factor and the C factor respectively. Then when you go into the next stage means continuing the equation, trying to find out the combination of 2, it will be tau into beta for factors a and b. Obviously, there would be a suffix tau beta suffix ij. So, I am not mentioning very explicitly the suffixes. Then when you are going to find out the effects or for combined effects for b and c, it would be beta into gamma, obviously with a suffix j and k, and when I am going for the combination of a and c, it would basically be tau into gamma suffix I into k, and when you are going for the combination of them, it will be tau beta gamma suffix I j k. So, if you note down here, I just highlight it. So, this was y I j k. So, there is only 2 factors here. So, if there were 3, it would be L here. So, mu would basically be the overall population average, taus corresponding to A, betas corresponding to B, there would be a gamma also, which is not there because we are considering 2 factors only. So, when I combine them tau and beta, which is tau beta suffix I j, would be combination of A and B. Now, this delta, if you remember, and obviously I will come to delta later on, this epsilon would basically be the error terms, which is epsilon I j k l if there are 3 factors, and if you note down that I is changing from 1 to small a, where small a is 3, j is equal to changing from 1 to small b, where b is equal to 2, k is changing from 1 to small n, where n is basically 4. So, this delta would be the corresponding the effect which will be coming out when you are basically trying to combine them and trying to find out the factors as such. So, I will repeat it, where tau suffix I represents the ground cluster effect, which is for A, beta j a factor A, beta j represents the filter type effect, which is factor B, tau beta suffix I j is the interaction, and delta k is the block effects which you are trying to find out, considering the blocks are done in such a way that if you want to divide the effects. So, you will basically consider one block and consider that to be non-deterministic or stochastic, such that all external factors are out of your control. So, whatever effects are coming out are the white noises. So, delta k is the block effect, epsilon I j k is the normally distributed error terms with 0 expected value, and sigma square the variance. Now, remember another thing, I know I am repeating. So, but please pay attention to this, the sigma square which I am taking are the error terms variance which do not affect each other. So, that means we are considering that the effect of error term from one time to the other are not there. So, hence it is basically the error term is not dependent on time. The sum of the squares for the ground cluster, which is factor A, filter type, which is factor B, and their interactions are computed in the usual manner. The sum of the squares due to the blocks is found out. So, you will find out the block effect considering y dot k or so, because k you are keeping fixed and you are trying to find out the sums for effect of factor A and sums for effect of factor B. And then the sum of the square of the blocks would be very simply given. I will just highlight the 2 formulas which I know that you know that, but still in order to if I repeat it, there is no harm in trying to basically learn it in more depth and trying to find out any queries which may have been left, and if you think you can write it to the forum, obviously we will answer that, but better if you basically understand it once again, the repetition would definitely help. So, we have the effects. So, technically this later point which I am now highlighting, which is y square, and dot means you have basically summed up for all i's, all j's and all n, that is factor A, B and the sample size, and divided by total number of observations is equal to A into B into n, and obviously in the initial term it is blocks. So, obviously blocks means you will keep k fixed and you will sum them up for A and sum them up for B, which is as done. So, I will to try to highlight using a lighter color if possible. Yes. So, this is the effect which I am talking about, considering that I find out the squares of dot k, that means blocks them and block them, and for each block I find out for all the i's and all the j's summed up and then divide by the the total number of observations. What is the total number of observations? For any block, the total number of observations would be summed up for all A, summed up for all B. So, it will be A into B. So, once I find out this value, I will just, so the value comes out to be about 402.17. So, you just put it, make a table, plug in the values and solve it accordingly. So, the complete ANOVA for the experiment is summarized in this table 5.22. So, in the table what you have is again repetition, but I am sure you will understand. The first column consists of all the factors and their corresponding effects taken 2 at a time, 3 at a time, as the case may be. The second column is the sum of the squares corresponding to these factors. Third column the degrees of freedom, fourth column is basically finding out the mean square error, and fifth column is basically f value depending on what your hypothesis is, and that is the ratios of the mean squares at different levels, and the last column basically gives you the concept of what is the value of the level of significance which you have set for yourself for the experiment or the ANOVA model, whatever you have. So, the table 5.22 indicates that all the effects are tested by dividing the mean square by the mean square errors. Both ground cluster effect and filter types are significant at a 1% level. So, it will definitely, the level of significance will change depending on the overall importance you want to give for those effects. Whereas their interaction is significant only at a 10% level. Thus, we conclude that both ground cluster level and as well as clutter level and the type of scope filter used affect the operator's ability to detect the target, and hence these values I will just repeat are the ground effect, which is A is 335.58, the degrees of freedom is 2. So, 335.58 divided by 2 gives you mean square of 167.79. Similarly, the filter type effects, the combination of A and B, which is G and F, the block effects, error terms and the total values come out to be as shown here. The degrees of freedoms are as shown here. Now, remember one thing, the sum of all the errors basically should add up to this value 2,047.83, that is 2047.83. Sum of all the degrees of freedom should add up to 23. So, this 2 plus 1 3, 4 5, 5 plus 15 is 20, 20 plus 3 is 23. So, this value basically is there, similar here. Then you basically divide the sum of the squares by the degrees of freedom, you get the mean squares, and finding out the ratios of the mean square gives the f values, and then you can basically comment intelligently whether they are significant or non significant depending on the level of significance. Now, we will consider the 2 level factorial design problems, the factors which I have been saying, that whether quantitative, qualitative, and basically consider them in more details within the 24th, 25th, 26th lecture as we proceed. So, as the number of factors in a 2 to the power k factorial design, so blocks you remember. So, factorial design problem increases, the number of runs required for a complete replication of the design rapidly outgrows the resources of most of the experiments. So, obviously, we have to take some corrective action and basically make our experiments foolproof based on the fact, and still conduct the ANOVA test and basically come up with meaningful conclusion. If the experiment can reasonably assume that certain high order interactions are negligible, obviously, so say for example, the effects of A and B are negligible. So, obviously, you can ignore that, hence the amount of calculation needed to be done would reduce, but you have to take an intelligent and rational decision to what level of significance you require the answer. So, hence neglecting some factors would now make sense to you. So, let me continue reading it. That certain high order interactions are negligible, the information on the main effects and the lower order interactions may be obtained by running only a fraction of the complete factorial model. So, rather than basically doing all the combinations, we will run only fraction of them, such that the level of significance for the experiment, not those values level of significance which you have set for yourself for the hypothesis testing, the overall efficiency is met, hence you are able to conduct the experiment and still get good results. These fractional factorial designs are among the most widely used type of design of experiments for products and processes in design, process improvement and industrial and business experimentation as required. A major use of fractional factorials is in screening experiment in which many factors are considered, and the objective is to identify those factors, if any, that have a large effects, and they can basically be not be ignored, but the small effects can be ignored, but obviously keeping in mind the efficiency of the problem. The three key basic behind ideas behind our successful fractional factorial designs are as follows. The sparsity of effects principle, this is important. When there are several variables, the system or process is likely to be driven primarily by some of the main effects and low order interactions, hence we basically should pay attention to that. The second important point is the projection property, which means the fractional factorial designs can be projected onto stronger, which means larger designs in the subset of the significant factors, as that even if they do not make sense in the overall scheme, but when you basically project it on, project means not mathematical projection, basically when you project it and try to find out the factorial effects on a lower scale, we get much better significant answers. Sequential experimentation means it is possible to combine the runs of two or more fractional factorials to construct sequentially larger designs to estimate the factor effects and interaction of interest. So, that means if you have considering that the factors A and B, the level of significance or the level of significance from the point of view of the sum of the squares is coming out to be very less, but once we combine A and B combine, or we combine A, B, C or whatever it is, the effects would come out to be much more significant, hence we should definitely not ignore them. So, sequentially we are basically trying to increase and trying to find out the overall effect, taking all of them separately, then we combine them 2 at a time, then 3 at a time, and go step by step to a higher level, such that we get a much more holistic and much more bigger picture for our analysis. Consider a situation involving 3 factors, each at 2 levels are of interest. But the experimenter, if he can actually experimenter has to do the example, they would be 2 to the power 3 values of treatment combinations, because the reason are there are 3 factors and each is at 2 levels. So, 2 to the power 3 is 8 levels of combinations we should basically find out. They however afford 4, they can however afford 4 runs. This suggests a 1/2 fraction of a 23 design problems, because the design contains, technically if you find out the overall effects, it will be basically 2 to the power 3 to 2 to the power 3 minus 1. So, that those factors to the power which you are taking is 3 minus 1, hence the total combinations of the experiment would be 4 in number and now not 8. So, that means you are basically halving them from from the original level of 8 to 4. So, which means a 1/2 fraction of the 2-3 design is often called a 2 to the power 3 minus 1 design. Suppose we select 4 treatment combinations A, B, C and A, B, C separately and A, B, C combined as our 1/2 fraction problem, and we can solve the ANOVA model accordingly. So, let us consider the effects. So, when we consider the effects factorial effects on a table format, so the plus and minus sign would basically give you to whether they are positive or negative. So, consider the treatment. So, the treatment combinations are, you have basically A, B, C factors done. So, when we are considering the fractional factors and 1/2 of the model, it means that we are trying to reduce the amount of computation which is required at our end. Rather than considering each of them separately or in a combination, such that yes, we will get the answer to the best possible extent, but amount of calculation needed to be done increases almost exponentially, because it is to the power, if you remember that. Now, let us pay attention to the slide which is in front of us, where we are trying to basically put the factors on the leftmost column is exactly in the similar way as we do the calculations, and then find out the combination of the effects to what level they are needed to be considered seriously for our calculation. So, the treatment combinations are individually A, B, C is taken. So, which is basically the first row, second row and third row. Then if we go, sorry, I will come to that. If we come to the combinations of taking 2 at a time, then we have basically the 5th, 6th and the 7th, and if I consider all of them combined, it is ABC, which is the 4th row. So, and obviously the value of I and the factors combinations are given as here. I will just highlight it. So, you have A single 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 single, this means only taken them into consideration. If I change the color, double means 2 at a time, A B A C A B C A B A C B C. Then you have the combined effect, last level, A B C A B C, you have the combined all of them I and I. So, now I will use a pen color with the level of color combination as orange and try to basically find out the effects. So, when I am considering the effects of A, let us go one by one. So, let us first negate one for which there is no effect. So, if you consider A's effect, it is not there for B, hence it is minus. It is not there for C, the level, and if I combine them, consider the effect of significance of A on a combination of AB and effect of A on a combination of AC are insignificant, hence they are minus here. And if we consider minus means we can put the picture in both the ways. The minus sign can be utilized to highlight an higher level effect or a lower level effect, whatever the combination is. Then if we consider the combination of B, so B would be minus for A, minus for C, and then if we consider C, it will be minus for A, minus for B. When I am considering the combination of A, B, C, this fourth column is positive for all the effects because A, B, C are there everywhere. Now, when I consider A, B, so obviously for A, B, if I consider the effects combined on of them on A, C is insignificant, of A, B, C is insignificant, and A, B, C is insignificant because for the case for the last one A, B, C, C effect is there. For the combination of B, C, B is there, but not A, and in K combination of A, C, you will find out the B is not there, only the effect of A. So, that is why they are minus minus minus, and this is obviously minus because it is only C. Similarly, when I take in AC, so let us consider where the minuses are. So, AC means AB minus because there is no combination of C, BC is minus because there is no combination of A, and ABC is there because there is a combination effect of C which is coming. When I consider AC with B, it is minus. Similarly, for BC, this will be minus, AB would be minus, AC would be minus, and ABC would be minus, and then you can find out the combinations of positive and negative. So, when I do the half fractional models of the 2 to the power 3 design, so you have the combinations as this. So, you have the effects of A, B, C drawn on 3 orthogonal planes. So, this is 3 dimensional. So, it will be easy for us to explain. If it is 2 dimensional, it will be on a flat plane, but is higher dimension, obviously it is difficult to us to understand. So, we will consider the effects coming out for C orthogonal, B orthogonal. So, they are orthogonal to each other and A orthogonal, and the combination if you do. So, if you are considering this plane, let me understand this plane which is in this room. So, if the wall which is at the back of me is the plane, and if I am standing at the origin, so on the right if you is A, vertically up is C, and or horizontally straight forward towards you, towards the camera, is basically B. So, the wall which we have here would only consider the combination of C and B. The wall on which, if I basically, if you see my picture on the wall back, it will only consider the combination of C and A, because B effect would not be there. And if I am considering the plane on the floor, it will only consider the effects of A and B, because C would not be considered there, because C is 0. And if I am taking a unitary cube, all the effects for A, all effects of B and all effects of C can be combined together towards the orthogonal line or the hypotenuse line, which is basically from the origin in to the point A, B, C, and you can basically do the mapping in similar way. Notice that the 2 to the power 3 minus 1 design is formed by selecting only those treatment combinations that have plus in the ABC column. Thus, ABC is called the generator of the particular fraction, and you can basically find out the effects accordingly. Usually, we refer to a generator such as ABC as a certain word. Furthermore, the identity column I is always put so such that we have the combination of I being equal to ABC. That means, we are trying to find out the combined effect of ABC, thus defining the relationship for our design. In general, the defining relationship for a fractional fraction, fractional factorial will always be the set of the columns that are equal to the identity column, which is basically ABC. So, in case if you have A, B, C, D, it will be a combination of A into B into C into D. If it is only AB, so it will be a combination of AB. So, in that case, coming back to the pictorial diagram which was explaining, the effect of AC would be only AC would be on the wall back. So, if there is no B, so all the effects would be found out from the origin, which is where I am standing, and if I find out the combined effect of AC, it will basically be the orthogonal the diagonal line going from the origin to the point on to the top, which will basically A into C. In case if I am only going to combine the combination of B into C, so A is not coming into the effect, it will be only the wall on the left hand side. So, here is the origin where I am standing, and the diagonal would be from this original to the point which is BC. Similarly, we can find out the combination of B into A would be the point where I am standing, and it will go diagonally along the floor onto the point which is basically B into A. Similarly, you can do the combinations accordingly, but obviously for higher dimension it will be difficult for us to understand for dimensions of 4 and higher. So, the linear combinations of the observation used to estimate the main results of fx of ABC would be coming out like this. It will be combination of A for only for A we want to find out. So, A has an effect on itself, yes. A has an effect on B, no. So, it is minus B. A does not have an effect of C, which is minus C, and once we find out the effect of ABC, it will be positive because A has an effect on ABC combined. When I find out the effects of B, it will be minus A plus B minus C plus ABC. When I try to find out the effect of C, it will be minus A minus B plus C plus ABC. Now, when I go to the linear combinations taken 2 at a time for BC would be, because BC means A is not there, which would be the effect would be for B and C combined, it will be minus minus because we are considering them separately. So, obviously, it will be minus effect. A would be coming with a plus and ABC would be coming in a plus. So, if you go to AC, it will be minus A plus B minus C plus ABC. If I go to AB, it will be minus A minus B plus C plus ABC. With this, I will end this 23rd lecture and continue more discussion about the effects of fractional factors and how they can be used to give us a better answer. Thank you. Have a nice day.